I lied. There we go. If you went to David Nelson's public lecture last night, you know that he planted his flag at the summit early in the evening there, but we're going to make the laborious ascent while we're here. So the base camp that we left off at involved a differential equation for the joint probability distribution that, other than for some sort of funny looking derivative operator, really looks just like diffusion. And in fact, it is diffusion on a sphere. So just to remind you of how things were set up, I'll copy the picture. What this is telling me is it's telling me the probability of observing a particular tangent angle, which I'll call T final, given that I had an initial tangent angle Ti, and that I've walked an arc length L down the filament. So, in other words, in the ensemble of thermal fluctuations, what's the probability that I observe this particular configuration plus all the ones that are equivalent to it as long with these things fixed? So in other words, I might imagine there's another curve that passes through here that also gives me the same tangent angles and so on. So these are exactly two configurations that contribute to a particular part of this joint probability distribution. And what we figured out is that joint probability distribution essentially behaves in a simple diffusive manner. What I'd like to do is turn this differential equation into a statement about the correlations between these two tangent vectors. So our goal is to compute the following thing. By translational invariance, I don't really care where I start, so I'll say this is 0, and I'm going to look at the thermal average of the dot product of the tangent at arc length s down the line with the tangent at 0. So that's the goal of the exercise. What I want to convince you of is that I don't actually need to solve this differential equation to get there. What I want to do is I want to convert this differential equation into a statement about a differential equation for the correlation function itself. And once I do that, I will be able to solve that differential equation and get the answer. So first of all, let's write down what we mean by this. I have an integral over all final tangents and all initial tangents back here. And here I have the product, the inner product of those two tangents. And this is multiplying g. Just made it in there. So that is the quantity that we actually want to know. You might say, well, this isn't quite right. There should be a probability that the initial tangent is actually at Ti, but that's going to be a constant, by rotational invariance. I don't really care what the initial tangent looks like, so I'm going to be missing a factor of 1 over 4 pi, which is just the normalization on the unit sphere. And I won't care about that because I'm going to fix the normalization when I solve the differential equation. So, someone mentioned the other day, Alex, don't you know about Boltzmann's constant? And the answer is I do, but there are too many things that look like k already. So whenever you see a t, you can imagine a Boltzmann's constant mixed in there. I made a mental note to make that point today, in case you were wondering. Fair enough. In fact, just to simplify things, I'm going to call this d for a little bit, which is like a diffusion constant, in fact. So the way I'm going to arrive at a differential equation is I'm going to differentiate this correlation function with respect to s. So of course, the derivative ends up on the only s-dependent thing here, which is the joint probability distribution. Gee, I'm going to leave off the arguments just for not running off the board, I guess, actually. Now, the advantage here is that I get to use the differential equation here to turn an s derivative into t derivatives. So go. So I get my diffusion constant out front, which we do need to keep track of if we want to get the thermal persistence length right. And now here I have t cross d by dt squared acting on g. And I'll put this to the top. In fact, what I really mean there is it's when the chalk gets wet that it crumbles so quickly. Yeah. Okay. In the integrand, what I really mean there is the following. I'm taking the derivative, eventually, with respect to the final argument here, the t final. And then when I'm done, I'm setting that equal to t final. And then as a final step, I have to integrate over this value. Now, here's the thing which I can do. I'm going to integrate by parts twice. So in fact, the integrated term vanishes, which you can, yeah, sorry. Yeah, so the question is, where did this derivative come from? Is that, it's paraphrasing. Yeah, so the idea is that I had a derivative with respect to arc length of the joint probability distribution, but I know that the joint probability distribution obeys this differential equation. So now what I can do is I can replace this by this. The advantage is now this is all t derivatives, and I'm integrating over t, so there's a hope there that I can do something slightly clever. And I should point out, of course, the cleverness is not initially mine. But we will actually get from things that the ancients knew to things that are, by the end of this lecture, at least relatively modern. So, in the integrand, we have this. And what we're going to do is integrate by parts. Twice. The nice thing is that the integrated piece vanishes. So in fact, the net effect is that the rate of change of the correlation function along the arc length between the two vectors in question actually is given by the following integral. So now what I've done is I've moved the differential operator from acting on g to only acting on this part, and I'm putting square braces around it to make sure that's obvious. And at the end of the day, the t, which I have here, has to be given by tf, and then one has to do an integral. Okay, so now we actually have traded a harder problem for an easier problem. The easier problem is we need to take this derivative of t, and that's something that you can work out yourself. It's, again, another one of these joys of the antisymmetric tensor. You can check. I won't work out the index gymnastics because I want to do other things today if I can. And it's actually just a little bit of vector calculus. I will leave it for you to check that the following is true. If I take the alphath component of this differential operator acting on the betath component of t, I end up with this. And if I do it twice, things get even better. So now I square this. we need the minus sign. We were happy we get the -2, so we get the 2 right. We'll agree with the thing. The minus sign is absolutely vital. Otherwise, we'll find the correlations don't decay with distance. So you better convince yourself that there is a minus sign, and extra credit is getting the 2 right. So if you get this far now, you're actually in very good shape, because you've converted what looks like a hard problem. Let me move this down to an easy problem. And in some sense, we've bypassed the whole issue of solving the diffusion on a sphere. So the net effect is that this is -2d. And now notice that what you're left over with, well, I'll write it right here. Can you read this? This is t sub I. It just ended up in a little cloud here. So there you go. And if you notice, this is exactly where we started. So you'll see that we have a very simple differential equation, actually. We have the arc length rate of change of the correlation function is proportional to the correlation function itself, so we know an answer. I slipped in an absolute value here because the correlation function has to be symmetric between s and minus s, and I had been implicitly assuming I have a positive distance down the thing to begin with, but I'll fix it now. I also slipped in the fact that I know the initial condition. Notice that there's a 1 here, and that's clear because if I set s equal to 0, I'm asking for the thermal average of 1, which, well, I'll check my calculator, but I'm pretty sure that's still 1. So there we go. So in fact, we see that the tangent correlation function has a simple exponential decay. And if this looks like diffusion in one dimension to you, you shouldn't be surprised, since we started with the diffusion equation to begin with. Now we just have to let the dust settle, put in what d is, and convert things. We end up with the final result, where Lp is simply kappa over t, and this is called persistence length. Ugh, thermal. Maybe if I had a bigger piece of chalk, my handwriting wouldn't be quite so atrocious. Then again, maybe not. There we go. So just to get a sense of scale, what is a typical thermal persistence length for a polymer? Well, if you have typical synthetic polymers, you actually only go a few carbon-carbon bonds before you decorrelate the tangent vectors. So you're talking about the scale of nanometers. If you're talking about filamentous actin, this number is almost 20 microns. If you're talking about microtubules, it might be on the order of millimeters, and how many millimeters is a little bit up in the air. So there's a very wide range. There's orders of magnitude change between stiff polymers and flexible ones. What does that have to do with what these things might look like? So in fact, people who think about stiff polymers don't ever talk about a bending modulus. They talk about a persistence length. So if you want to know how stiff something is, people quote you a length, not a modulus usually. So let's try to get some intuition about what that means by converting that into something that you could picture. We also heard last night in the public lecture that if you were to look at a polymer, you might see that it looks something like this. If you have a stiff polymer, you might imagine it looks more like that. And if you have a very stiff polymer, you might just see something like this. So this would be persistence length increasing. One thing that we can do to quantify this sort of art here is to talk about the end-to-end distance of the polymer itself. So we can label the two ends, draw a vector from one end to the other, which I'll call r. Because of the rotational symmetry of the problem, r's average doesn't help me. So the first thing I can do is look at r squared. So we'll look at this, which is related to the radius of gyration, is what people say. Let me pull up the next page here. So let's think about how we're going to calculate that. The thermal average of r squared has got to be the, well, let me write r first, and then we'll talk about the average of it. I'll do it 2 steps. So for any given configuration, if I know the set of tangent vectors as I walk down the chain, I can simply integrate them back up to go from one side to the other. In other words, if I have some curve like this, here's s equals 0, here's s equals L, I can calculate the end-to-end vector as the sum of tangent vectors as I walk down the filament. So if I want to compute r squared, I know what to do. And if I want to average it, I need to take the dot product of r with another copy of itself. So I need to be a little bit careful. I actually have a double integral, and I need to keep track of 2 versions of the dummy variable for the arc length. And what I'm left with is actually the same tangent-tangent correlation function that we just computed. So now we're in the business of doing a simple integral here. You can keep track, so I guess I just make a note that this piece we're going to replace by the absolute value of s minus s prime over LP. In the interest of time, I'm going to just tell you the answer, but you can do an integral of an exponential too. So in fact, what we find is the following. 2LP, let's write it like this, I guess, L, and now I have 1 minus LP over L times the quantity e to the minus L over LP, like so. So look, first of all, when you get this result, which obviously I just pulled out of my hat here, you should at least ask yourself, does it make sense? One thing, the sort of the dumbest test you can pass is it dimensionally reasonable? Well, this is a length squared. This is a length squared. This is a dimensionless term. The other thing you can ask is, do the limits make sense? If the thermal persistence length is really, really big, what should happen? Or if the thermal persistence length is really, really small, what should happen? In other words, does that result agree with our intuition in interpolating between this picture and this picture? So to check that, we can do the following. We can imagine that the length of the polymer is very short compared to the thermal persistence length, which I call this rod-like. In which case, of course, you can now look at looking at doing an expansion in a small parameter. You will find, I think I'll skip the algebra here too, because I want to get to the finish line here. I'll put in one intermediate step, which is really just a signpost for you when you're checking your math. So notice that if L is much less than LP, this is e to something which is very small, so I can expand that around 0. The 1s cancel, and then the leftover stuff gives me this. Yes, I'm sorry, question? Comes from a 1/2 x squared. Let's see. Yeah, and then you have some cancellation. You had a x squared term. It comes from the following. E to the minus x is 1 minus x plus 1/2 x squared. And then, yeah, okay. Yeah, then this cancels, yeah, exactly. So that's the first non-vanishing piece that you get. And it has the advantage, you'll notice, of knocking the persistence length out of the problem. And in fact, what you get is you get L squared. And you get corrections that go like so. So what is this telling you? It's telling you that it's essentially a straight line. The average of r squared is L squared. And these corrections, of course, better be negative because the little residual fluctuations you have to pull the two ends a little bit closer together. So, well, I think I'm beating a dead horse here, so I will move on to the next limit. Although, just as an aside, if you are going to beat a dead horse, having a stiff polymer is probably a good place to start. Just occurred to me now. So the other limit is we can say the polymer is very long compared to its persistence length. Flexible filament. In which case, you can check that we get the following. Which seems a little bit weird, first of all. But you can write this in a slightly different way. I'm going to write this in the following way, which actually I think matches David's notation from last night. So we'll write it like so, where we've introduced n to be L over 2 persistence lengths, and B to be 2 persistence lengths. So what is this saying? It's saying that at this level, you can treat the squared end-to-end distance as being that of a random walk that takes steps of 2 thermal persistence lengths and takes n of them. And essentially, we took the original filament, which has length L, and we counted the number of independent directions it can go by breaking it up into a bunch of little pieces of length 2 LP. So what we've done is we've taken this picture and we've turned it into a picture like this, where these are 2 LP long, and there's no correlation between one and the next, and to lowest order, that's what you get. Of course, there'll be correction terms here, which will come in at higher order in LP over L, that presumably will make this a little bit longer, because actually there are some residual correlations here that we're neglecting in this limit. Yeah? Yeah, that's okay. So the question is, why is it 2 LPs and not 17 or 1, for instance? Frankly, I was always bothered by the fact that there's a 2 there, but in fact there is. Because, well, I would have said that here you have a smooth decay of correlations. There's a natural length scale for that decay, which is LP. Why is it that the lowest order term here requires you to think of these as chunks of 2 LP long and not just LP long or pi times LP long? I don't know. Yes. So you're saying that if I'm sitting here and I walk 2 steps down, then this one has absolutely no connection. If you think of this as sort of a weak hinge, and actually, we're in the limit where this hinge is completely free, though, is the funny thing. So I guess what you're saying, I'm sorry, I think I'm saying your thing wrong. I have to break this piece up into 2 little pieces of LP long, and you're saying this hinge still has some sort of residual memory of the original direction. Yeah, I probably that's why the number is greater than 1, but I don't know how to turn that into a statement that it's 2, other than doing the math. But I think that's... I agree with your discomfort to the number 2 in front there. But then again, I would say, what's a prefactor of order unity? Yes? Well, if I want to get if I want this to be the right limit, which in fact it is, and if I want to turn it into a statement about a random walk of vectors that are simply completely uncorrelated, I have to choose what's called the Kuhn length. And it turns out that this microscopic parameter that goes into your random walk statistics has to be 2LP long if you want this formula, which is what you'd expect, to agree with this formula, which is what we just computed. That's my entire point. Yes, another question. No, that 2 is the 2 that showed up there. And that 2 canceled out the 1/2 that shows up over there. And this 2 actually is also related to dimension, but so is that one over there. But this is a one-dimensional diffusion problem. But if the tangent vectors live in d-dimensional space, you do get a different number there. You get d-1/2, it turns out. So I don't think I repeated your question. Sorry, Leo, I messed it up. Can I continue now? Yes? No? Well, you're sort of stuck here until the rain lets up, so. Okay. I think we've said enough about random coils. Okay, so can we actually do something new with this? Well, what I'd like to do is specialize to the former case, where the filaments are short compared to their own persistence length. So we can talk about what people call the business of semi-flexible filaments. What I really mean here is that the length is at least less than or maybe comparable to the thermal persistence length. In other words, if I were to look at one of these filaments in a microscope, and in fact you can fluorescently label an actin filament and look at it, you're not going to see this. You might see this and you might see this. That's the limit that we're going to talk about now. So the nice thing is that all the hard work we did to talk about the mechanics of actin or DNA or any stiff rod, when we really torture it, we bend it in a tight circle or we twist it and do all these things. Now it becomes much simpler because we're only interested in these very gentle sorts of bends. So in the small bending limit, we have a couple of simplifications in the mechanics that are helpful for doing the statistical mechanics in the next step. Let me try a bigger piece here. So first of all, this is better. We can think of the tangent vector derivative with respect to arc length, which is the second derivative of the position with respect to arc length. We can replace this by the second derivative of the position with respect to the lab frame z coordinate. So in other words, if we have a filament poking out in the z direction, but it just wiggles a little bit, we can ignore at this level the difference between following the arc length, which is what we should have done, and following the z-axis, which makes our life a little bit easier. So as soon as you get to do that, you can go back and calculate the energy of deformation of the rod, again ignoring the torsion term. We can write this over as an integral over z, and now this part is easy. So you can think of this as two comparable pieces, and if you like, you can think of these as two different transverse polarization states of this wiggle. So you can imagine wiggling the filament in the x direction or in the y direction. And the two at this order, the quadratic order, are now completely decoupled. So yes, question? U's are the, I'm sorry, did I not? I can't really remind you because I never told you. Thank you for pointing that out. I guess U is going to be the displacement vector, as a function of z describing the state here. So as I walk down the z-axis, I have presumably a small vector that now wiggles around and gets bigger and smaller and tells me where the filament is in that xy plane at a given value of z. So in other words, if you were to look down on the thing, it would be the distance away from the origin here, the vector distance away. And I'm breaking it up into x and y pieces, and the two are now independent. Okay? So we can now compute the equation of motion in this simplified limit by looking at the first variation of the energy with respect to a wiggle. So what I'm going to do is I'm going to drop one of these guys because they're obviously the same. Let's just concentrate on, say, the x polarization to pick one. And I'm going to remind you that the Young's modulus times the moment of inertia tensor that we needed is we called kappa now. And in fact, we can consider a circular cross-section for simplicity. So I1 is equal to I2 is equal to I. So if you do that, you're going to be looking at an integral of the form dz squared ux plus delta ux squared minus, of course, this one. So notice we're obligated to integrate by parts twice to get the delta u out by itself. Go back here. So, okay, let's do this. It's not quite the right system, but now I'm going to use the underside in all of them. It's not the canonical way, I guess. So integrating by parts, of course, is another way of saying what we're going to get a surface term. So we're going to get boundaries. I will do if we integrate by parts, we will end up with the following. The first variation of the energy is going to be kappa d by dz squared of ux in this case times delta ux prime, which now is evaluated at the two boundaries, which is L and 0. There's no light on this one, right? No, okay. It was such a good trick, I thought I'd do it again. There is one more boundary term, which is now 3 derivatives on u times delta ux evaluated on the boundaries. And what's left over is an integral. And we have, of course, 4 derivatives, like so. And all the integrals are dz at this point. So there we go. And if we wanted to include a force, and I'm only going to be considering forces that are perpendicular to the undeformed direction of the filament, we would have added a term to the energy of the form like so. And you can see that the first variation of this just gives me an extra minus f floating around here. So the net effect is that if I want to set the first variation to 0, I actually get statements about the differential equation obeyed by u, which is going to be this. And I also have statements about the boundaries. In fact, by dimensional analysis, we can figure out what the boundary terms mean. Notice that everything here has to have dimensions of energy. This is an angle. This is in this lowest order in U description, this is simply telling me about the tangent of the angle that the filament's making, which for small bending is the same as the angle. The thing conjugate to the angle and the energy has to be a torque. So this has to be an end torque here. So we can identify. Can you read this up here? No? Easily fixed. Torque. So this has to be a boundary condition on torque. So you have a couple of options. You can specify the torque at the boundary, in which case you're obligated to let this be free and do what it needs to do, or you can specify the angle at the boundary, in which case you're obligated to let the torque, constraint torque, be what it needs to be. This, you can see, is a term where you have a displacement times something is an energy. This has to be a boundary force. So just like we talked about with bending the DNA, you can imagine taking the end of the DNA and putting a torque on it or pulling on it. And that's the case here. All right. So, and then of course in the center of, or the bulk part of the problem, you have to obey this differential equation. Yeah, that's right. I'm not pulling along the axis. I am, if the rod's like this, I'm pulling up on it, pulling down on it, doing what I want. And of course, there's the equivalent term for all the y's, but it's no news. It's sort of weak T to write that one down because it looks the same. Yes, yeah. It's a big prime. Yeah. Okay. And so you can see, in fact, that we have 4 boundary conditions coming out naturally, and here you have a 4th order differential equation, so in fact it all is copacetic. You get everything you need to solve the problem, and that comes out naturally from doing this integration by parts. So, well, they have 1 on each side. Yeah, so I get 2 here plus 2 here. Yeah, right. No, it's probably small things amuse me, but you have this thing which by integration by parts generates the 4th derivative. It naturally generates the right number of boundary conditions for you, and for some reason that amuses me, so I thought I'd say so. Okay. Okay, there we go. So I think, let's see, how am I doing on time here? Good. Doing okay. So in principle, you can solve all the sort of small bending mechanics that you might want to, although probably, well, I'll do one quick example. Bending mechanics before we try to go back to putting in temperature. Well, you'll notice that if I don't apply any transverse forces, then this whole problem becomes fun with 4th order polynomials. All solutions have to be of this form, and you have 4 unknown constants, and you have 4 boundary conditions to set them, so it's all now a matter of sliding off a log. Just to pick sort of a weird looking one, you could imagine setting you could imagine setting the angle at 0. You could imagine setting the angle at L to vanish, and you can say that the displacements on the 2 ends vanish as well, and you can find the appropriate solution, which you can check as the following. If you plot that, you of course have to sort of launch the filament at the angle you chose, alpha, and you have to pin it on the 2 ends here, and you'll find a solution that looks something like that. Comes in flat because I required it to. So you get, and you can amuse yourself, in fact, you can amuse yourself for the rest of this hour while I'm babbling on by making all kinds of funny shapes if you like. But let's do something more interesting than making funny shapes. Let's ask the following question. There's all these musicians in the audience. Imagine you had a tension-free stringed instrument that had a bending modulus, and it was thermalized, and you were to look at this system. You say, the string's fluctuating thermally. What can I say about the statistical mechanics of the deviations of this filament from being straight? So we're going to need this if we want to think about pulling on the filament in a minute. Let's see. I guess I have to start erasing now. Oh, did I skip one? Okay. Oh, God. The problem is that by the time I figure out this clever system, I will leave this room again and never use it. So how are we going to do this? Well, if I know the energy of any particular configuration, I can write down a Boltzmann weight for that particular configuration and then sum over all configurations and get a partition sum and go from there. So I'll just take, again, one polarization state. I'll use primes to mean derivatives here. It just simplifies the math, or it simplifies the writing. And I'm going to take my boundary conditions to be such that the filament is pinned at the two ends. So I'll look at all kinds of states that look like this. So the way I can do that is I will expand U in terms of sine waves with an, as so far, unknown amplitude, like so. And then I can plug this into my energy. And a little bit of work will get you to the following. I think I'll skip a step or two here. It's pretty clear where the n to the fourth comes. Two derivatives gives me n squared, then I square it. And that's going to be the key feature I need. And the rest of this is just an squared. So here, I guess I should draw all kinds of different configurations that I'm allowing. There we go. So the partition sum, z of this, is going to be, I guess I wrote n. I'm going to allow the amplitude to be arbitrarily large, although I'm going to have a Gaussian energy, so I won't really care about what happens for very large A. And here, this is T. And here I put my energy. N to the fourth, an squared. OK. So by the equipartition, oh, yes, question. Well, I require it to be 0 on these two ends. So I can, by Fourier's theorem, write down any shape I want here by expanding in sine waves now. Well, it has 0 energy, so I can certainly add as a 0 energy term here, but I'm not going to see it. So, and if I'm going to, and also if I compute any thermal average of U, it won't contribute to any sort of function of U. It's just going to give me the 0 piece. So I think I can skip those. So what I know now from this, of course, is all of the amplitudes are 0, which is simply a way of saying that they're equally likely to be positive or negative. And the only correlations are between the same one and itself. And if you work out the arithmetic, you will have 4, 4, and 4. Most of this doesn't matter. The n to the fourth matters a lot. If you want, you can rewrite this in a slightly more transparent way, which is 2L cubed over a thermal persistence length times pi to the fourth over n to the fourth. So you can see the bending term strongly suppresses the high wave number modes. So we go back over here. And now, unless there are magical boards I'm not aware of, I have to erase. Let's see. Okay. So you can ask, well, now since we have the partition sum, we can ask ourselves anything we choose. The thing I computed is I said, well, what's the average of u squared as a function of z going across here? So to compute that, I have a sum, a double sum on n and m. And I have the thermal expectation value of an sine for the nth mode and am sine for the mth mode. And of course, the only thing that actually has a thermal average is not these, which are simply sine functions, but the a's. The Kronecker delta over there collapses that into a single sum and lets me write LP. And again, the n to the fourth makes a big deal here. In fact, you're dominated almost entirely by the n equals 1 mode. If you want to plot this, you can. And what you'll find is that u squared as a function of z looks something like the square of a sine, which looks something like that. And in fact, if you go to this point here, you'll see this peak is only a few percent higher than it would have been if you just took the n equals 1 term. And that's because 2 to the 4 is 16 already. So things go downhill very quickly for you. So you'd think there's not a lot there. There's not a lot of wiggles to have. How can this be at all interesting? After all, it looks like you basically just have the filament doing this back and forth, and the little wiggles are really strongly suppressed. I'm going to try to convince you, though, that I would say naive intuition doesn't hold. And in fact, most of the mechanics of a semi-flexible filament under tension, it comes from pulling out these small thermal ripples that don't seem to do a lot if you just look at it, but actually give you a small reservoir of length to play with to give you some extensional compliance. So, let's see. I have it's a height squared, L cubed over LP. So, but what I'm yeah, exactly. What I meant is that if you scale this by all the prefactors here, you basically see mostly the n equals 1 term. That's right. If it is, the whole point is I have to work in the limit that LP is the biggest number in the problem. Otherwise, I can't go to my small bending approximation. So yeah, if I were to graph it in such a way that it looked physically reasonable, you wouldn't see much. So this is an expanded scale, if you like. And I've done that by multiplying by this. Thank you for pointing that out. So, okay. So let's pulling on a filament. And this is mostly taken from Macintosh case and Jamney, I think it's 95. So the basic question is the following. Take one of our semi-flexible filaments, where this is the z-axis, glue it to the wall here, and of course it's going to have some sort of small wiggles to it. Now imagine grabbing it with a bead on the other hand or otherwise, and applying a tension tau to it, and asking how much does this point move as a function of tau? In other words, what's sort of the Hooke's law, or going beyond to a nonlinear response of this filament? So that's the question. And I'm going to assume that the filament itself is not elastically stretching. In fact, when you do this with actin filaments, the extensional compliance is very well approximated by assuming that the filament's effectively inextensible, except you have this thermal reservoir of length that you're depleting by tension. So it turns out that this inextensibility condition isn't so bad. Let's Let's erase this. Let's see, how are we doing? So how are we going to think about this? Well, one way to do this is the following, is we can say that imagine you were to apply infinite tension, you were to, or freeze the system to t equals 0, so it goes completely straight. That would give you some length, which we'll call L infinity, where the infinity reflects the fact this is the infinite tension limit. However, at finite temperature, the filament actually takes up less space, or has less extension. There is a difference here, which we'll call delta L. And really what's happening is that this delta L reflects the fact that I'm using up arc length to wander around a little bit. And as I apply tension, what I expect to have happen is I expect this delta L to get reduced until it approaches L infinity, at least asymptotically. Okay, so that's the game plan. The question is, how do we do that computation? Well, to start out, we can say the following. The total arc length of the filament is L infinity. And I can write that in terms of this integral along the filament, which using the fact that we have small bending, I'll expand the oh, yeah, sorry, I forgot what I was doing. Yeah. So, same words, same equation, better location. I had gotten to here, expanding the square root. I have the following, and that means that my delta L, which is L infinity minus L, is just 1/2 the integral of the square of u prime integrated over dz. So what this is saying is that exactly the amount of wiggles that you put in it is depleting the length of the filament and pulling the end point in. If we want to write down an energy, which we need to write for our partition sum, that incorporates the tension, it has to be conjugate to this length. So what we have now is we can add a term to the energy. And I'll pull this back down in just a second. And again, I'm neglecting the fact that there are two polarization states. You can see where that matters, actually. There's exactly two independent copies of this. There's a ux prime and a uy prime. And they both suck up just as much length. So in fact, I have two equivalent reservoirs of length to deplete. So at one point, I will multiply by 2 to take care of that, but not yet. So here we go. Here's the energy. And you can see that as I increase the tension tau, I'm going to increase the energy of states that have larger angles, in other words, that use up length, and then suppress the probability of observing those states. And by suppressing the probability of observing the more wiggly states, the average position of the end will move out. So it does the right thing. Given that it does the right thing and that it's about 5 minutes to the hour, should we do the 5-minute break? Okay. I'll be right back. Okay. Well, how about I get back this going again here? Okay, so we have this energy now as a function of tension. We can do exactly the same sort of Fourier sine series, which gives us the energy now as a sum over the same Fourier modes, where the only difference is I've added a term proportional to the applied tension that's now quadratic in the wave number and not quartic. Like so. Good. So I can now compute the following quantity. Remember, what we really want to know is we want to know what happens to delta L as I change tension, tau. So I'm going to compute the following thing. What I mean by this is, what is the thermal expectation value for delta L, the amount of arc length, that I'm using up in wandering around so I don't get it in the z direction. And I'm going to work in an ensemble where I fix the tension. So you could imagine that I hang you could picture it something like the filament's wobbling around like this. I have it going over a pulley, and I have mg hanging down here, so it has a fixed weight. Yeah. Yeah, so imagine, I mean, I know this is a little bit silly and artificial, but imagine this was an actual thermal system. What would you see? You would see the weight bobbing up and down a bit as the thing pulls in and out. And you could ask yourself, what's the thermal expectation value of the position of the weight, for instance, which is related to the amount of length you've used up. Because after all, as this thing crumples up, it lifts the weight. It's not, in fact, this is exactly the same sort of entropic elasticity as David Nelson talked about last night, where you heat the rubber band and it pulls the weight up. The difference is, of course, is that the wiggly things in his problem were in the flexible polymer limit, but the idea that you use up extension and gain entropy by wandering around more is exactly the same idea. We just have to count things a little bit differently. The energy of each state now depends on the wiggles, whereas in David's problem, the energy was irrelevant. Each state had the same energy. So, okay. So the nice thing about this is that if you recall, this piece was just the integral of u prime quantity squared. So in the Fourier domain, this ends up being, you have to be a little bit careful about 1/2, but that's it. You will end up with the following. That's really what we want to know. And if you work this out, you'll see that it looks like there should be terms that couple an and am, but of course they have to vanish. So when you look at the thermal expectation value, this is what we need to compute. And we've been through this once before, so I think you know how to do the answer. The equipartition theorem tells you to put t in and divide by this and 1/2 in your set. So, in fact, that's just a way in words of saying that I know that when you put all the factors together, you end up with the following. Like so. So now I can combine these, and what I have is I have delta L. I will drop writing the tau here at each step. In principle, I should put it in, but it seems a little pedantic after a while. This is, in fact, equal to there's a 1/2 here. T, which is, T is the thermodynamic temperature, and again in units of Boltzmanns if you like, or I've gotten rid of KB. Here I have the q squared in the numerator. Downstairs I have a q4th, and a q squared, so I can clean this up in just a second. And at some point, I might as well get the right answer. Remember, there are two reservoirs of length, and I only accounted for one of them. So, in fact, I can multiply here by 2 to get both polarization states. Okay. Go. So remembering what delta L meant, we can say that the thermal expectation value of the z extension is going to be equal to, in this limit, L infinity minus something which is positive definite, which is very comforting. And with the cancellations, I have the following pieces. So it's easy to interpret this. This is the total length that you could have had minus the length you're using up in the undulations. So this is the used up length. So we have to figure out how to do this sum. We'll come to that in just a second. Before we do, though, let's take a quick look at these terms. If I were to look at individual terms in this sum, as a function of n. In fact, I'll do this on a log-log plot. Do log. Yeah, sorry. Y is what dimensionless? Delta L better not be dimensionless, right? Delta L better have dimensions of length. In fact, let's look at L here and make sure it has the right dimensions, okay? Oh, you're saying I just made a mistake. Oh, I need to have a, let's see. Oh, you're saying I don't have enough powers of L here. Let me see. So, oh, I'm missing an extra L, I guess, coming in here. Well, because I had u squared, u prime squared. See, so I was integrating a u prime squared. So that is a, no, that's right. So that's going to be a dimensionless piece. So what am I missing? I guess I'm missing an L here. There. Thank you. Sorry. And I guess the same then factors through the whole way. So I throw it here. Sorry about that. And I guess I need one here too. Well, oh, I think I've already taken care of it by the time I got to here. So let's make sure I like this. This is a force. This is an energy, so it's a force times a length. So by the time I got to here, I sorted my L's out correctly. So sorry about that. That's a good catch, though. OK, so now we're in good shape, I think. Notice what happens here, though, is that when for sufficiently large tau and small n, this thing really is basically just t over tau. That's the amount of length that, sorry, it's in the shadow. This is t over tau, really, each one of these terms. At some point, though, I'll hit an n where this thing will transition over to going down as 1 over n squared. So in this log-log picture, this is a slope of -2. So in a sense, you can see what happens as I increase tau. This transition moves farther and farther out. So what it's telling me, really, is that the small n modes, the sort of gentle bends, get pulled out first, and they get pulled out so that they essentially subtract this much. They subtract only this much length. The other ones, you'll notice that as n gets larger and larger, this is the amount that they're subtracting gets smaller and smaller here, right? So the point is that as tau gets bigger and bigger, I get more and more of this stuff, right? So I'm going to start getting closer, and as tau gets bigger and bigger, I am depopulating these thermal undulations in a wave number dependent manner. But the net effect is that even when I sort of saturate this out, it still is inversely proportional to tau. So as tau gets bigger, I end up with less and less pulled out. So not only am I getting back length, but I'm depleting the modes differentially as I go. So you should be able to observe the tension in a filament by looking at the changes in the statistics of its wiggles. And in fact, people do that. So now, how are we actually going to solve this? Well, one thing that you can do in a simple way is we can ask the question, in the small tau limit, we can have a well-defined Taylor expansion in taus. So let's consider that problem. So we can actually get a nice-looking answer. So first of all, let me pull out the T. I don't care about the temperature at the moment. We'll get it back where we need it when we're done. So what I'm saying is the first step is to write this as tau equals 0. So I have the sum of 1 over n squared, and I have some factors here, plus the first order correction in tau, which is the sum of 1 over n to the 4th times L to the 4th, kappa squared pi to the 4th, and so on. I can keep going this way. In fact, we'll can keep doing this. Fortunately, each one of these sums is, well, obviously convergent, and in fact can be written down in closed form. Let me go over here and do it. So, in fact, this sum is going to be pi squared over 6, which is the sum of 1 over n squared from 1 to infinity, kappa pi squared, minus tau L to the 4th, kappa squared pi 4th, and then this one ends up being pi to the 4th over 90. And if you work even harder, you can do the next one. We'll get the first. So if you like, this is the equilibrium amount of length pulled out before you apply any tension. This is telling you how that length is getting depleted linearly. This is the Hooke's law piece of it. And then this is the first nonlinear correction to that. And this number ends up being pi to the 6th over 945. And if it was obvious to you that the sum of 1 over n to the 6th is pi to the 6th over 945, I congratulate you. But in fact, you can work them out. So what does all that mean? When the dust settles, as it were, and we take this result and we plug it back in, we see that the thermal equilibrium average of the extension in the z direction is not the full extension, but minus a little bit. We talked about the fact there would be corrections to this rigid rod of this type. And in fact, the number that we didn't know before is minus 1/6 here, it looks like. Then the next correction is this. And then the final correction that I computed, anyway, is this one, kappa cubed. So again, this is equilibrium, this is linear response, and this is the first nonlinear term that you have. In particular, the part, this in a way isn't terribly interesting to us, because we'd like to know what was there a question? I missed some. No. We're not really interested in the equilibrium length. If you don't do anything, we'd like at least the linear response. So with this coefficient is what matters, really. So in particular, you see that tau goes like delta L times kappa LP 90 over L to the 4th. So this you can read as F goes as X delta X K. So in other words, this is the Hooke's law spring constant that's purely entropic in origin. And you know that because there is a temperature built into LP. So in fact, it all has to be there. Yeah. Yeah. No, it's absolutely true. That is the energy of any configuration that you choose to name. Now what I did is I computed the partition sum. The log of that is the free energy. Well, minus the log of that times T is the free energy. And that I could now compute, in fact, but instead I jumped straight to working this out. But you can easily go back and write down the Helmholtz free energy as minus KT times log of that garbage over there. And you're set. But no, you're exactly right. That's a good question. Notice something that's important. It'll be important for looking at a network of these things, which is how we'll finish up, I guess, is that if you make the filaments longer, the spring constant gets dramatically softer. And the reason is that as you make the thing longer, you have a lot more wiggles to pull out. And in fact, it's the sign here you can also guess. You'll notice that the material is getting stiffer as you go, which also makes sense. What we're seeing is a force versus extension curve, which I just called delta x. What we figured out is that it comes in here with some finite slope, which we just computed. And in fact, as we pull harder, I called this tau. I shouldn't change my mind all the time. In fact, this curves up. In fact, you know, if we really believe the filament's inextensible, this has to run up a singularity. When there is some point where you hit a critical delta x, or delta z, which corresponds to L equals L infinity. At that point, there's no more wiggles to give. And so you have to go to a vertical tangent at that point. So you have some sort of curve like so. So in fact, the local spring constant of the system, in other words, the local slope of this curve, depends very strongly on a very small amount of extension. Or another way of saying it is it's highly nonlinear. If you pull a little bit harder, it's very easy to make the thing stiffen up dramatically. This seems to be the reason why these semi-flexible networks can harden quite dramatically by about 2 orders of magnitude when you turn on molecular motors. Essentially, at least our understanding of it currently, is that the molecular motors take you from being an untense network, where your slope here is like this, to a highly tense network where your slope can be orders of magnitude larger. So essentially, you pull out some of the thermal slack, and the system becomes remarkably stiff. Yes, in fact, the shear modulus does go up. I sort of switched gears on you. I meant if in the network, if you have a random network of linear springs and you just crank up the spring constant of all of them, the material stiffens by that factor. But in fact, that is a good transition. I'd like to at least sketch for you what happens if you now do this in a network. So can we actually go backwards and take the filament, which itself is the output of a linear elasticity calculation, and treat the filament now as the atoms in the system, as the microscopic elements, and then say what's the collective mechanical response of a whole network of cross-linked ones. Okay, so you can imagine a network of these filaments, something like this, and it should be a random network. And what I'm going to do is I'm going to ask the question, if I shear this system, where this angle I'll call theta, what is the stress response of the system, or equivalently, how much elastic energy did I input into the system for a given amount of shear? So what we're going to do is we're going to do a type of mean field calculation. We're going to say every single filament in the system simply gets rotated and elongated in this direction, and every filament that's pointed this way gets compressed. And I'm going to assume each one is still in the linear response regime. So we'll be talking about a small strain, not actually what I drew, but maybe a 1% strain or even less. So the key point is that a given filament under this deformation gets stretched out like this, a little bit delta L. Fortunately, if we know how much it's stretched, we also know how much how much tension is now on the filament. And we're going to assume that this works for compression as well, so we don't have to worry about what direction this is going. The key point that connects the microscopic deformation to the macroscopic imposed one is that any segment of filament that we're interested in between two crosslinks is simply going to be extended so that the extension is proportional to the original distance times this strain. So what I mean by LE is the mean distance between crosslinks. So if you were to stand on one of these filaments and start walking and keep track of how far you go, this would be the typical distance you would walk between this filament is chemically linked to another filament somewhere in the network. So you can imagine there's little bits of glue in here holding this all together. So we have kind of a random woven set of bamboo sticks. Okay, so we need to characterize the density of these sticks. The way people talk about this is they talk about the density of length in the volume of the box. So a length density is going to have dimensions of 1 over length squared. The way I like to think about it is you can take all the filaments in the box and organize them however you choose, keeping the mean the same as long as you keep the same volume of box and the same number of filaments. In particular, if you were to place the filaments on a square lattice so they're all poking out at you, you could ask what's the distance between two of them, and we'll call that xc, which is also known as the mesh size. So we've introduced a couple of new ideas. One is the mean distance between crosslinks, and another is the mesh size, which will be in fact the typical distance between here and here. And you can imagine what is called a densely cross-linked network where these two numbers are equivalent, and we'll talk about that as the simplest case. So what I'd like to do if I want to calculate a modulus is I imposed a particular strain and I'd like to calculate a stress. Well, my stress, as we're now all familiar with, is a force per area. So typically, there's going to be one filament piercing an area of size the mesh size squared. So the typical amount of stress that I should see, and I'm not worrying about geometric factors about exactly how it's pointed. I'm assuming that I have a statistically isotropic system, and in principle I should average over angles, and that would give me some factors of order unity that I'm going to ignore. So I will have this ignoring those factors, Gesundheit. And now, taking my result from pulling on a single filament from the top board here, and using the fact that delta L is LE times theta, I arrive at the following result. Make that a 3. There we go. So where's the modulus in this picture? What I want is an expression that looks like the following. Strain times modulus gives me a stress. So just collecting terms, I see that G better be all the stuff here that is multiplying theta to give me sigma. So I end up with the following result. Notice this is very different from what you get with a flexible chain. If you have a flexible polymer, the entropic elasticity, which was also mentioned last night, is just T over this mesh size cubed. And you notice this, essentially you have only one length scale in the problem, which is now going to be the mesh size in the gel. And you know that the only energy scale, since everything is entropic, has to be kT. And the only thing then with dimensions of energy density is T over a mesh size cubed. That's a simple way to think about it. Notice that's not the case here. If, in fact, we have a densely cross-linked network, which allows me to get rid of... I'm sorry, yeah. Did I? Probably I did. Either that. I should have kappa squared, so why do I... Oh, I have LP floating around. And see, oh, notice that I have kappa LP there. So then if I remember LP as kappa over T, I get kappa squared. I went back and forth like that with absolutely no thought in mind other than to confuse you. So, you know, sorry. Yes, it should. Okay, there we go. Thank you. So densely cross-linked. Then what we'll do is we'll say that the typical distance that you have to walk between crosslinks is the same as the typical distance that you'd have to walk to run into the next filament. We can do that, and in fact, we find that the modulus goes as kappa squared over T times xc to the minus 5th power. So typically the way this result is expressed, though, is not in terms of the mesh size, but in terms of something which is more experimentally accessible, the concentration of actin in the system, or the concentration of polymer that you have. It turns out, and you can work this out from geometry, that think about long straight sticks, you can convince yourself that the mesh size in fact is proportional to 1 over the square root of the concentration. And dimensionally this doesn't look good, but in fact there's a hidden factor of the radius of the rod that goes in there to fix things. So that does the job. Notice what that does for you is it tells you actually that the modulus of a semi-flexible network actually grows with concentration as the 5/2 power. It goes faster than linearly. So that, in a way, is a little bit surprising, because naively I would have said, if I take a box full of springs and I hook them up in some way, and I think about the modulus, I would need to know the spring constant of the springs, but I want to know how many springs essentially cut a plane, because that's the number of forces per area that I have to worry about. You would expect that if I increase the concentration of springs, the number of springs would simply scale up linearly with that. Here you notice that if I increase the number of segments of semi-flexible filament by decreasing the mesh size and increasing the concentration, this grows faster. The reason is that this effective spring constant gets stiffer. Not only do I have more springs, but each spring is effectively stiffer. Why? Because all the cross-linking has quenched more of these undulations, and I have less stuff to pull out, so it gets stiffer. The way you see that is you see the power of L that goes into the effective spring constant. So you actually have a material that, as you change its concentration, it gets stiffer, I would say dramatically more than linearly here. And then the other factors you can pretty much guess at based on either dimensional analysis, well, actually dimensional analysis, and realizing that the only modulus that we actually really worried about was the bending modulus. So with that, I think I'm supposed to be done. I wanted to say 2 words as sort of summary. What I hoped to do was, well, you'll laugh. I had hoped to do sort of the same story now for fluctuating membranes and calculate the mechanics of that. Obviously, I expected to talk twice as fast as I did, but that's the way it goes. Those notes I will be sure to give to Leo to get posted should you want to read them, and if you don't, well, in fact, it goes for all of them. It's up to you. But they'll be there. The picture that I was trying to present, or the thing that makes this coherent to me, is the idea that we started from a elastic theory that ignored the internal details of the atoms. And that's actually what Tom developed in the beginning. He says, well, if I don't want to know about the Young's modulus and the Poisson ratio, I can start by writing down a continuum description of the material. We then said, well, if you actually then talk about elastic elements that have at least one small or perhaps two small dimensions compared to the other one, so either filaments or membranes, you can actually lump together the elastic constants into new effective mechanical coefficients that control the bending and stretching of this material. And then we said, okay, now we keep packaging. We then say, well, once we do that, we can talk about the mechanical response, in this case under extension, of a single semi-flexible filament in thermal equilibrium, and turn that into an effective spring constant to talk about a network of those. So we have this idea of sort of packaging and repackaging of internal structure into a single number, which then goes into a larger scale theory. And at the end of the day, we've developed a calculation for a modulus, which I said we weren't going to do actually in a sense, but it's not the modulus based on the internal atomic interactions of pieces of actin. It actually has to do with some sort of collective behavior of filaments themselves. So we've actually now developed a theory where the filaments themselves become the atoms at the next level. So at that point, in principle, you can go on and do more complicated things with networks that have that are not merely random isotropic ones, but ones that have bundles, distributions of bundles, pneumatic order, and all kinds of things that are interesting, but there's certainly no time for that. Anyway, I'd like to thank you for your attention, and there you go. Yes?
So in this nice formula that you then applied to actin networks and so forth in the upper middle board,
Yeah.
Is that L infinity? Is that the first term? Is that the same as L?
Yeah, so the difference between L and L infinity. Yeah, so it's a little bit funny. If you go back to here, what I've done is I said I'm integrating along the z-axis a particular distance. I'm going to compute the amount of length that's used up in that piece, and then I'm going to add that on to L to tell me what L infinity would have been.
So L is the projected length.
Yes, that's right.
You could have converted that expansion into all L infinity by a little bit of L.
If I'd chosen to, yeah. Yeah. Why is the stress? Oh, well, I need, tau, I'm sorry, I didn't understand the second part of what you said. Oh, because so think about it like this. Here is a sheet. Imagine I make a cut in the material, and I have some number of filaments poking through this. Oh, maybe I can do it. Poking through this cut, right? So what I need to do is I need to say I want to compute the total force acting across this cut or this plane. So what I have is the xc squared is telling me the area, the typical area that's occupied by one filament. If I put them on a square lattice, I would have one filament going through a square of this area. So this is telling me the geometry of the number of filaments per unit area I would have. And that's what I need there. Now, if I want to know how stiff my filament is to extension, then I have to go back here and say the right thing to do was to say that this was LE. So that's why that one appeared here. And now you can muddy the waters a little bit by saying, you know something? Every time two filaments come near each other, I'm just going to imagine they're cross-linked, which they say is a densely cross-linked network, in which case these two numbers are comparable. Certainly to within the order we're working, we might as well set them equal to each other at the end. But that's where the distinction lies. Are there any other questions? Yeah, Leah. Yeah. Yeah. Second and third. Yeah, that's right. Yeah. Right. Yeah, so, well, you have to remember this is a small tau expansion. So it's not clear to me that I want to use this to decide how to get back to L infinity. So all this is telling me is that at tau equals 0, this is telling I've used up this much length, and now I've pulled out a little bit, and then this is the first nonlinear correction. But in principle, if I wanted to know those things, the way I've set it up is you would have to actually do the sum with the tau in the denominator. Yeah. I think that's the answer for that. But it's actually a good question. I haven't thought about that, really. Yes? Mm. Yes, that's.
Can you think of any? I guess. Can you think of any industrial or commercial applications where affect processing?
Well, this might be my shortest answer. No. I don't actually know the answer to that question. It's not that I don't think there is. I can't guarantee you that there are no industrial applications but it's hard. Apparently, it's hard to synthesize semi-flexible polymers. Yeah, it's probably very true. In fact, most of these. See, the reason as we talked about, the reason these things are stiff in a sense is that they're not single carbon-carbon bonds, but they're actually compared to an atom, it's a big protein. In fact, it could be a cluster of proteins. So if you look at a microtubule, it's something like 14 or 16 dimers of tubulin going around a ring. And if you look at actin, it's a pair of actin dimers that wind around each other into a helix. So it's the reason these things are dramatically stiffer than synthetic polymers is you're not actually looking at single carbon bonds. So I think that's probably why the route to synthesis of this is difficult, although I'm now out of my depth. So, yes? Yeah. Yes, I certainly want that. If I'm not in that limit, then this whole picture of small bending breaks down for me. So in fact, if you wanted to imagine, if you were God and you had a dial that turned persistence length however you chose, you could go between a typical flexible polymer gel where you have a random walk of polymer between two points where they're tied together, to this case just by cranking the LP up and down. Although it'd be kind of funny if you cross-linked in the flexible limit and then made them stiff, you'd have some sort of weird stress built into the system that I wouldn't know how to think about just yet. But yeah, does that answer your question? Good. Well, at least there's a great persistence in questions, thermal or otherwise. All right, well, thanks again.